Hey everybody, Dave Johnston here again with AggressiveFun, and today we are going to explore some robot arms that I've had for a while. Here's the intro to our family of 7+ a little brother robot arm. Check them out. That's our family of arms. These robot arms I've had for quite some time, and I am wanting to, you can see it there, I want to make a controller for them. Today we're going to do a teardown. We're going to do a review of what we see here as far as the mechanics and the motors, and then look at how I can end up building a controller. I'll show you the controller in a little bit too, and we'll do a teardown on it as well. Turns out that I bought these, and then I have one other one I'll show you here in a minute that is the little brother of these, that are where it's called the Microbot Alpha right here. And it was used more for colleges and training courses, and those university courses, those kinds of things where you've got these robot arms as the hardware that you would then program. This particular arm and the other 6 that go along with it, I was told that they were used by Intel, and I'll show you. They came with different types of grippers. This particular one, you can see, is for a wafer, an integrated circuit wafer, before they've been cut into the tiny integrated circuit die. So I tend to believe, I got them off of eBay, I bought all 7 of them at the same time with one controller, and my hope was that the controller, it's a huge box, and like I said, I'll show it to you in a little bit here. But my hope was that it wasn't one controller and now I've got 7 arms, and I've got to figure out how to control 6 of them because I have no controller. In looking at it, it had a whole bunch of connectors coming off of the bottom of it, and so I thought, oh, well, this isn't so bad because there's probably a connector for each one of the 7 of these arms. Well, it turns out no. The huge box is for one of these guys, and I only have one of them. But turns out that it's so old, I don't want to use it anyway. And so going forward, this is going to be the first part of a multi-part exploration of these arms, not only mechanically and the servo motors and driving them and figuring out how to make the grippers work, but also in coming up with new controller electronics. So today we're gonna get a little bit familiar with the mechanical parts of the arms and see how the old system is, and we're gonna do a teardown on this one. And then going forward, there will be a Raspberry Pi, there will be an Arduino controller, and an interface in between whatever processor we choose. We need to have driver electronics that can drive the stepper motors inside. So that's kind of the overall plan. This first part, like I say, is going to be a part 1 with all that other information coming in subsequent videos. I wanted to show too, hopefully I can, these are kind of heavy, hopefully I can get it up there. There's the tag. This is our Microbot Alpha from Microbot Incorporated, Mountain View, California. Made in the USA. This is serial number 1131, so they made quite a few of them, it looks like. I got all 7 of them on a deal with the one controller off of eBay several years ago, long time ago. And I was told at the time that the 7 were integrated into a system for Intel in a clean room type environment. Given the gripper of a wafer type, I tend to believe that. I didn't get any other information on them, and when I got the controller I was really disappointed because I only got one of them, and It has an RS-232 interface, but there's no software, there's nothing. So at this point, I don't know that it's worth even trying to make one controller work for one arm when I've got 7 of them. And I obviously, at some point, I'd like to control them all at the same time, do a little show, do some little thing with all 7 of them operating at the same time. Maybe I'll do a line where one hands off to the other. I don't know. I'm open for suggestions. You can leave suggestions in the comments down below of what you think I should do with all 7 of them. Some kind of coordinated show. Don't know. Totally open for creativity on that one. So, with that, let's get started. Now, these are, with this small of an arm, I think the term still applies as far as exoskeletal, meaning that its structure or its covering on the outside is the structure. So hopefully you can see inside of there, this is all hollow. There's nothing in there. It gets all of its support from these 2 units, or these 2 sides, that then have the main pin for the joint comes through the center of rotation here, and it rotates about that one. So my point with all of that being that we only want to tear it down so far, given that you can see that there's a cable drive here. So you've got tendons that go up through the arm and get to the point where they control the gripper, and they control rotation as well, which is a pretty interesting feat, given that you've got 2 tendons pushing and pulling down here. Mechanically, then they have to wrap around a shaft up here that then can make it so that it's controlled in rotation, and that's going to make it so that it doesn't have constant rotation. A lot of robots in their wrist joint can rotate continually. This one can't, because there again, you've got 2 cables with a limited amount of length that they can move, and so this guy, it's at 360, looks like 720 degrees rotation, which you could deal with. You certainly aren't going to screw in any screws continuously with that, but to turn things over and whatnot, that would be a good amount of range. So let's take off this cover up here on, actually first let's do this cover right here that we can see. When I first got it, the gyro aspect of it, where you press a button and it doesn't do anything except turn the light on, but it detects your wrist rotation. At first I thought, oh, it's going to be really cumbersome, I'm not going to be used to it, I won't like it. But in the end, man, I've fallen in love with this thing. You can also do it in a pistol grip type arrangement if you want to do it that way. I prefer the other way. But it just has become really convenient, easy to use. Nothing can stop us now. I'm wondering about the screw in the middle. It looks like it's holding maybe a strain relief. And that, it's kind of, oh, I didn't like that sound. It's kind of odd that they would make that blind like that. Yeah, it was the strain relief. And then this, and it does. You can see inside there's all of these different tendons that go up to the arm, or to the features at the end of the arm. Now there's one tendon here in the middle. Hopefully you can see this pulley right here. It actually pivots and there's a switch on it, and hopefully you can hear that click. There's a little micro switch that is not doing its job right now because this tendon is loose. And it's loose, it's come off of the wheel right down inside of here. If I pull on it, it definitely has to do with the grip. Well, and I think it's when the gripper gets to a point where it has exceeded its amount of force, that it then trips the switch down below and makes it so that it saves the cable, and the cable won't break or come off of its pulley then. Let's go one step further here. Let's take off this cover on that one cable. Since this is exoskeletal based with the structure on the outside, we can take these covers off. It doesn't change anything because the outside of the housing is the main structure. Okay, this will come right off. Oh, there's lots of mechanism here. We have an optocoupler sensor here over this lower pulley that has the switch on it. That it came off. You can see this wheel. It wasn't in the right place. So if we rotate that around, the gripper, you can see the gripper closes, and then with that in place, then it goes through and works for the switch. It definitely works for the gripper. There's something else wrong there though, I'm not quite sure. You can see the tensioners here to make sure that these tendons stay tight. They use these tensioners that have an attachment to the end of the cable, and then you would undo the lock nut here and change that if you wanted to make this tighter or looser. And you can see them move there based on how the gripper's rotating. And then you have the other direction. You pull them both at the same time. That'll be interesting to see how they do that down below, because the first impression is if you're doing this, that would take 2 motors. But if you're doing this, those 2 motors have to stay in sync, which is still doable from a control point of view. So you have the wrist rotation, wrist flexion and extension. Okay, so these two are controlling that. That falls off when these are spring loaded, and there's springs up inside, and then there's a spring that's supposed to keep everything tight that you can see on the inside there. This particular sensor, if I take this cover off, it's this piece. This this arm doesn't move. This guy is what moves, and it spring loaded here. There you go. If what it does is, if you're completely, we'll say, extended on the wrist and rotated all the way to one side, that breaks the opto switch and detects that it's at a stop in 2 different directions. So then when you reverse it back the other way, it would let it operate normally. When you're all the way extended this direction and you get all the way to the other side, it then triggers it again. So it protects the wrist. There are 2 plastic tubes right here, and there are 2 little ports right up in here. I don't know if you can see that or not, but they come out the side. There are these 2 screws on the side. So they had some screws in there so that you don't release pressure without something connected, but it was made so that you could attach something up here that had to do with air. Maybe it was when you were picking up one of the wafers, maybe you could do that with suction versus a gripper that clamped onto it. Okay, that's enough on the arm and wrist and gripper. Covered all of the little sensors, where all of the linkages go, and all of the cables for that one. So next, let's dive into the base, and there's the two half pieces here. I'll take both of them off quickly. This one will hopefully slide right off. and you've got 3 motors, 3-stepper motors on this side, 4 wires. Basically, when you go back to the workings of stepper motors and servo applications, you would have a motor like this, and the way that it's set up here is just open loop, meaning right here anyway, it doesn't have an encoder attached to it. It could have an encoder attached to the back here, or a different type of position sensing device, and from that it would know where the motor shaft had turned, because it would mount to the back of the shaft, which there's a hole here. You could mount it to the back of the shaft. With a stepper motor like this, at least from the motor itself, you don't know where it's at when you turn power on. So it's basically open loop. It's at a particular position and you can start moving it one way or the other way. Now, when you have a joint or in a robot, or you have a motor that's just trying to control some active surface, with a motor you need to have a sensor that can tell it where it's at. You can use absolute encoders, which will, the minute that you turn the power on, it knows exactly where it's at, because the absolute encoder has a disc that's the full 360 degrees, and the disc has a pattern on it that at every step in the resolution of that encoder, it can tell exactly what the orientation is. That's an absolute encoder. An incremental encoder only counts pulses. So an incremental encoder does not know where it's at when it starts, but typically they have an index pulse built in. So when you start up a joint like this, you would very slowly move it to a particular position until it sees that index pulse. When it sees that index pulse, it says, aha, I know that I'm X number of degrees away from center, and from there it knows so many steps are a certain number of degrees in one direction, certain number of steps are a number of degrees in the other direction. So the index pulse is critical. With this, I see we have a sensor here, another optical sensor. It's a slotted switch, and hopefully you can see right here where my finger is, there's a slot that, or a little tab that goes into the slot. So when it's all the way back like this, it breaks the beam between the emitter and detector on that slotted optical switch and says, hey, I'm all the way into this position. So that is the index point for this joint. So when it powers up in your code, you would have to say, okay, I'm going to rotate in this direction slowly because I don't know where I'm at, and as soon as I get to the point where it breaks that slotted switch, it says, aha, I know where I'm at. So that's very cool. Every one of these joints will have something like that. I'm not sure on these other smaller joints. They're definitely not up here. Now, they may be using this other mechanism up here. My guess is when it gets clear around to that spot, it knows that it's just driven it all the way that way, and this guy gets pulled down. Oh, wait a minute. It was all the way in one direction, and then it's, well, see, in that case, you can make this guy actuate just based on rotation. Okay, so that will be, and the combination, what you know then at that point is how you were making it turn, and you knew there procedurally, I guess you could get away at some point with using that as your index pulse for both of those. It would have to be a particular procedure though, because you have to know where it's at for that to be broken. I noticed that there's a lot of slack in this cable that controls the gripper. If you pull on it, it works like normal, but there's so much slack in it down below here that it doesn't stay where it would detect, it falls off of this pulley as well. So when we get further down in, we're going to determine why that guy's going loose. Now also, while I was looking at this, I noticed that there's another slotted optical switch here, that this guy, that it's mounted to this plate, and the plate moves up and down, and because then this guy hits this one and makes it stop in the other direction. So my guess is there's two motors there, and either one of these make it so that it breaks. Like right there, it would have stopped. It said, whoa, I've gone too far, depending on the position of this guy, or you can hit it there. So it's a programming issue. They've put in place some things there that need to be monitored with software. Okay, so now we are on to the next area, which we could do this other side. So let's take this one off, see what we can see inside of this one, and it should be the same as what we saw on the other side. So you have three motors, three-stepper motors. Oh, I was going to read off what these say. This is a slow send synchronous stepping motor. Slow send is very common stepper motor manufacturer, been around forever. This is a 200 steps per revolution, pretty common number of steps per revolution. 0.44 amps, 11.2 volt, and they're all identical. All 6 of them are the same. There's not anything else you can see from that side. Let me take this front plate off. We'll see what we can see inside of here. We'll be able to see all of the gearing and the belts. Take that cover off. The arm, there's a rubber piece that goes across here, so when the arm comes back, this is its stop. And some of these belts have fared better than others. You can see the strings on this one. Belts have really deteriorated. I would guess that these others that are in better shape were actually changed out at some point, or maybe they're from a different batch. Whatever the case, they are very old. You can see how they actuate. There's a piece, extension piece with a gear. These are all toothed belts. I don't know if you can see that very well, but these pulleys have teeth on them. The belts have teeth. They mesh together, and then there's this gear here has those same teeth, and the extension off of the motor shaft here then makes it so that it's in its right spot. Same thing with this one. The motor further to the back, these two go to these two on the insides. The next one's in, and then the far outside ones go to these two motors, the ones that are furthest down. And then each one of them has their cable, and they're tight, except that one. I bet that one's the one that is our problem up above. So they're tight. They have anchors down here in the bottom. You can't see it, but there's an anchor where the other end of the cable comes down and anchors there. One thing that you have to take into account with this is rotation affects rotation. What you're seeing, there's 6 motors, right? So there's got to be 6 degrees of freedom. Meaning this is 1 degree of freedom. This is 1 degree of freedom. Then you've got the elbow, that's 1. The wrist has 2 because it has rotation and it has extension and flexion. Extension and flexion are just 2 different directions of the same joint movement. And then you have the gripper. So 1, 2, 3, 4, 5, and the bottom is 6. So 6 degrees of freedom, 6 motors. That's why when you rotate this, that motor's being rotated, that belt is moving, is because that's the one that controls the base movement. And that's no doubt that's why this particular belt is in such bad shape, is its it's moving the most weight, the most mass of any of them, because it's having to rotate with all of the motors on there. It's not lifting them, but having that rotation is a lot of strain. Okay, so you can see how all of that works. Get a better view here. On this pulley wheel, this cable that goes up to the gripper has fallen off. It's gone over to this side, and it's wedged down between. I don't like how the cables can easily come off the pulleys, because the pulleys themselves don't have any sides on them. They're relying on them being close enough together that they'll hold each other in place. And I got news for you, that does not work. The pulleys with no edge on the pulley to keep the cables always in place, that's the biggest downfall. And I could see when you're machining the pulleys like that, it's going to be a lot harder, a lot more expensive to machine them with an edge. The last section on this guy is the base and whatever is under there. It's going to come out. Oh, there's quite a bit of circuitry right here. It is the smart move that you would have all of the drive electronics on this end close so that your cable here doesn't have to carry a lot of current. We have 12 stepper driver controllers. It is a PVL 3717, and they are monolithic IC drive zone phase of a bipolar stepper motor, and has all kinds of capabilities built in. Sense, resistor, comparator input, and so that's why there are 2 per motor. Okay. Oh, and these other boxes, I'm not able to find what they are. They're very expensive, but I don't find a description. So I believe they're a DC to DC converter. It says 36 volts DC, and then you've got a couple of LM339 comparators. So that's it. Here's the controller that I got one of, and I was very disappointed. I knew I was only getting one, but I didn't know that it only controlled one arm. Now you can't see this, but you can see part of it. The part that you can see is the plug-in control module board up here at the top. But the main controller is this huge printed circuit board. Now, I was hinting earlier that we could figure out the date and how old the whole system was. On the board right here, they've got silkscreen 1982. On the EEPROM, which this is a 2716, it says copyright 1982. So I think it's pretty obvious this was built in 1982, so it's quite old. And it has a 6502 processor. And any of you who are familiar with the Apple II computer knows that the Apple II runs on a 6502. So it's got a 6522 parallel peripheral chip and a 6850 Motorola, I believe that's the serial controller, baud rate generator, all of that for serial communications. And then they do have a 1488, 1489 driver pair chips for RS-232 in and out. Now, one thing I mentioned earlier too, as you can see down here at the bottom of the board, there's what, 1, 2, 3, 4, 5, 6, 7 connector. And so I hadn't looked at it real close, but I remembered there were a lot of connectors that came out the bottom, and I thought, oh, 7 connectors, there's 7 arms, maybe there's a connector per arm. Well, no, there's one box. This whole box is for one arm. So you have a robot connector, the big one like we just saw at the base of the robot. You have P2 auxiliary motor, which one goes to something else, P1 auxiliary motor. This is teach control, which I never did have. Operator control, computer, and the one on the end there is peripheral. So I've never powered this guy up. I don't know if it would work. I do want to connect it into an older laptop that I have that still has a serial port, and I'll see on power up if there's anything that scrolls in a terminal program with just serial data, and see what streams out when you turn it on for the first time. We can also take out the board. You have a line filter right here, terminal blocks for the main power, but no doubt that's 5 volts. 6502 ran on 5 volts, and all of the other circuitry that's on this board. This is an Acopian, and this would be the 36 volts for the motors. And that's all there is to it. To not disappoint, maybe that's too late, but regardless, we have Microbot Teachmover robot arm. This Teach pendant has all of the functionality on it. It says train, run, closed, enter, and mode for the indicators, and then they have B, S, E, so that must be base, shoulder, elbow, P, and G for the gripper. You have a mode, stop, and a mode, and a record. So this guy is actually set up where you don't, it does have the computer connections there. Again, I'm sure for RS-232. And you can still program it without being connected to anything with this thing. Now, turn power on, nothing moved. That's good. Look at that. I don't know how many years it's been since this thing is run. Okay, we'll do a quick little program here. Okay, so we'll say that it was there. And I'll pick it up, move it, move the elbow. Run. So, pretty easy to record. Okay, that is our teardown review and look at the controller for the Microbot Teachmover, as far as the one that runs and is the trainer, and the Microbot Alpha, that is the power horse, I suppose. One side note here, it is kind of encouraging that each robot arm has its set of 12 drivers already underneath. So driving with an Arduino, driving with a Raspberry Pi or a Beagle Bone, or whatever the microcontroller may be, is simplified. I don't have to lay out a whole controller board. All I have to do is figure out the interface between those boards and the base connector on the arms, and then it's a matter of software. So I was thinking I'd have to lay out a brand new board to control each of the stepper motors. Looks like I may be okay that way. It's just a matter of figuring out how to drive them with the connection that's now from the old controller. That's going to be much simpler. So I'm encouraged. That's going to happen in part 2. Not sure where I'll go from there. Part 2 may be with one of the boards, maybe an Arduino, and Part 3 could be with the rest. Either way, the next part is going to have the arm running. Maybe Part 3 is an animated show with the 7 arms, and then maybe this guy in the show somehow as well. And that's where, again, I need some input. If you got any clever ideas what to actually do with all 7 of the arms, feel free to leave comments, questions down below the YouTube video. Very encouraged. I do read them all, and I appreciate any feedback that you leave that way. We also appreciate any subscribes, likes, thumbs ups, all of those kinds of things. Hopefully you enjoyed what you saw here, and I'm always open to any kind of feedback. The website is a work in process, but it's getting much better. It is just simply AggressiveFun.com. We do all kinds of things on there, list all of the videos we've done. There is an e-commerce site in the works for selling of electronic components, solder, consumables, all of those kinds of things. There's also links to all of the tools and anything cool that I can think of that I've used, my favorite solder choices. All of those kinds of things are listed there as well, just to give you an idea of what they are. But also, most of them have links to Amazon, where you can then purchase them off of Amazon. Makes it very convenient for you, and I get a little bit of a sales commission for directing you in Amazon's direction. So, with that, thank you very much for watching, and we'll catch you next time.